Good afternoon, everyone. Thank you for attending my talk. Today I'll be presenting on cache-aided networks, and the title is deliberate. It's not a typo, from practice to theory. And hopefully it'll be a bit clearer as we go along the presentation why that is the case right now in the academic world to a certain extent when studying these types of networks. The work I'm going to present is a joint effort with Dr. Ravi Tandon, who is my co-advisor, and also with Dr. Sai Dhiraj Amuru, who was a PhD student here. Most of you know him. And also, we have recently collaborated with the NJIT lab of Dr. Osvaldo Simeoni and my advisor, Dr. Charles Clancy. As far as the outline is concerned, we'll just get started for lack of time. So, to introduce caching, it is motivated by the paradigm shift that we have seen recently in content-centric networks. So, going from 1G, 2G, and currently to 3G, 4G, and on to 5G, we have seen that the nature of wireless traffic over the air has undergone a drastic shift to become more content-centric and packet-switched from the circuit-switched nature that we observed mostly due to voice calls earlier. And smartphones have led to a big change in this pattern since multimedia content is distributed heavily on handheld devices nowadays. And I guess this graph right here has replaced the well-known Cisco graph showing how mobile will consume video. So 5G is the buzzword nowadays, so I also put a 5G graph here, and IoT is another buzzword. And all these things contribute to the content-centric nature of traffic. And as we know, it's going to be an exponential growth in traffic. There is a massive increase in scale and capacity of such networks, so scaling is very important. As well as the fact that we need to increase the network efficiency to deal with such kinds of traffic. Now, I agree that there are many various directions in which this research can go when you start looking at ways to increase capacity. Spectrum sharing is one thing we at Virginia Tech are big on. But the kind of work that I'm going to suggest here mainly focuses on the fact that you basically utilize the current network elements that you have in order to increase the efficiency rather than moving into a paradigm shift of a different wireless access or file layer technology. And the main key point here is that even content-centric traffic over mobile networks is inherently temporal, and it has a lot of variability from user to user. And another important point when studying these networks is that of late, storage or cheap storage has become ubiquitous. So it's not that difficult to incorporate storage into network elements. And as we go along, we'll see that this has been a key to a lot of the new network architectures that have been studied in industry as well as in academia. So why caching? As I said, user demands are highly temporal and non-uniform. And this can be leveraged to basically prefetch some content and store it at the users or close to the users rather than at the network center. And cache placement basically is mostly performed at the time of low network load. For example, we can perform cache placement during the night when the wireless traffic is low. And you can look at cache placement and complementary delivery as a kind of load balancing effort rather than any sort of a very drastic network change. And so after you place some content at the users, you hope that the users request some of these popular content. So you need to be careful and smart about what you place. And once you have placed such content, you want to make sure that the users request those contents and you make a complementary delivery during times of high load so that you basically reduce load on the backhaul network. And that is where the load balancing comes in. So this figure I put on all my intro slides. This is work that has been done by the Virginia Tech Spectrum Observatory, and especially by this guy, Dr. Abdullah. He's now at Intel. So he gave me this figure and he showed me that this is basically 1 day's observation of a downlink frequency spectrum. And you clearly see that there are various periods of inactivity and activity. And we can, with caching, we hope to utilize these periods of inactivity more so that we can store content here and bring this red region to a more yellowish region. Well, everyone's not as lucky as US Cellular. No one uses it here, so it's always yellow. But the main goal of this work in general, or the studies of this nature in general, is to find out theoretical and practical guarantees which endowing some network elements with storage and doing this caching and complementary delivery can contribute. So essentially, we are looking at some theoretical guarantees on content delivery, as in rate or latency, and we'll come to those as we go along. So Now we start about cache-hidden networks, and we look at a very simple topology where we say that we have a centralized base station, um, and these base stations are connected to maybe some network edge elements, which we call small cells here, but it could be any network edge element. And we say that these base stations, basically during times of low network load, place some content in these small cell base stations. And we assume that these network edge elements have some storage associated with them. And also, the inherent assumption is that we have some idea of what content is popular. We'll talk a lot about that in this presentation specifically, but supposing we are given an idea of what content is popular, I know what people in this room will request, I can then make an informed choice of what to place, say, at a base station which is serving just this room, for example, so that when you request that content, it doesn't have to be downloaded from the main base station.
So
and
in this graph, those backhaul links, those dotted lines, are
Yeah.
those wide or are those
It doesn't
lines?
matter. It doesn't matter. For the purpose of this study, it doesn't matter. As I will talk about it more, we'll see that there are levels of abstraction which you can use. You can make assumptions on those links or not. But for all practical purposes, it doesn't really matter. You either way want to reduce the load. So generally in such a network setting, it's microwave links that connect these. They're still wireless, but they're line of sight microwave links. And as we move towards more involved heterogeneous networks, we envision that there'll be more of an underlay overlay type of situation where we are using the same license spectrum to do the communications. So one important aspect about this system model is the fact that you proactively cache at the base stations. That is, the caching itself needs to be independent of the user requests, because you can't just place something and then when the requests come in, if you don't place properly, then what ends up happening is you still need to download from the main base station. So the caching needs to take into account what sort of requests the users might make, and you need to place proactively before the requests come in. And as I was telling you, the best case situation is there is no backhaul load. These caches will store content smartly enough so that you can download everything from these guys. But again, best case scenario is not always the case. So we'll talk about the main challenges. One is, as I said, sensing for these caching periods. The figure I showed you is specific for this town, for example, but if we want to come up with a general policy, you need a way of knowing when these caching periods occur, and they may vary quite drastically based on where you are caching, right? And then the next most important question, I believe, in caching networks is the fact that what is the best way to estimate the file popularity? Because content is inherently temporal in nature. Things change all the time, right? So there should be a very formal way of estimating the file popularity profile. And as I will mention at the end of my talk, many of the theoretical aspects of caching consider that this popularity profile is already given to you, which is one thing which we talk about next. Another, obviously, the most important challenge is once you're given this popularity profile, or once, suppose you have estimated this popularity profile in some way, how do you utilize that popularity profile to place content in the caches? Do you do a centralized placement, a decentralized placement? Do you do coupled, decoupled? And there are many concepts of coded or uncoded, which we will come to later. And finally, file delivery. How do you want to deliver the file? So once you have placed the content in the caches, these guys request some level of content from these small cell base stations, right? What is the best way to deliver the files to these guys? So obviously, as you can see, I've included a pretty well-connected network here. So obviously, network topology plays a big role. And what do you use? Do you use point-to-point transmission, or could you do something smart by utilizing multicast transmissions, which is mainly the topic of the information theoretic aspect of this problem? Or you do groupcast delivery. So those are like some of the options. But these are mainly the 4 challenges that we have in cache-aided networks. So I'll talk a bit about literature and what people generally study. So caching at higher layers, which is the kind of work I do, is mainly focused on how to place content or what content to actually place in the caches. And there are a few frameworks. Femto caching is a celebrated framework which came out of UT Austin. So they looked at how to place content in the small cell base station caches so that you can minimize the overall delay. But that was also looked at from an optimization perspective. And I'll tell you the distinction later of how information theoretic caching, for example, differs from that. And then the topic of today's talk is learning-aided caching, how we can introduce the idea of reinforcement learning into these cache-aided networks. And finally, the new buzzword again in 5G is fog radio access, and what fog radio access is and how it basically relates back to the current system model that I'm talking about. And I've got a lot of collaborators here whom I've already mentioned, and those 2 guys on the left, they are basically my gurus because they started the whole concept of information theoretic caching based out of Bell Labs, and we started this work based on some of those concepts. And here we have another great researcher who basically focuses on the next level of caching, I believe, which is mostly to do with how the users are served by the small cell base stations. So this kind of work basically abstracts away what we work on, like the cache placement, but they are more interested in finding out how the interconnection in the network and how the coverage probabilities basically scale with the number of users in the network. But obviously there should be a good overlap between these concepts. And this study is very important, I believe, for practical implementation of these networks because we often abstract away the file layer completely. As I said, this talk will focus on more of a femtocaching framework, and I'll come to that later. We'll talk about reinforcement learning, and we'll talk about optimization for cache content placement. And finally, we'll talk a bit about collaborative caching. And by collaborative, I mean, can you do something interesting when you have multiple base stations? First, I would like to introduce a very basic learning-aided framework. This was introduced by Dennis Gunduz and Paul Blasco in ICC 2014. It was a very nice paper. So basically, the idea here is we'll look at a simple network with one base station and one small cell base station. The users are connected to the small cell base station. Now, what we would like to do is we would like to proactively place files in the cache and then look at the user requests and see if we satisfy the demands of the users. And how we will proactively cache is based on a learning mechanism. And the learning mechanism basically goes on between the base station and the small cell base station. So you look at user requests over time, you observe what sort of requests are coming in, and then basically you try to estimate the popularity profile of the file library that you have.
So do you assume that you are given a file library?
Yes, that's what I was coming to next. So we assume that we have a set of files. And I think this is a realistic assumption under the learning setting. We'll talk about the information theoretic setting where the file library needs to be necessarily smaller, but it could be arbitrarily large here. Generally it's realistic because, for example, Netflix, if the central server is supposedly Netflix, and this is some edge node near your city or something, Netflix will generally look at what sort of content the users around that area are consuming, and they'll place from that set of files generally. One or two files, outliers are always there, so one or two files coming from outside these libraries are generally served by the main base station, but that does not contribute to the main load on the backhaul. This is a bit of notation that we need. So firstly, we have a library of F files, say, and each of the files have a different size, assuming that we can divide it into bits. So there are S1 to SF bits, and those are the sizes of the files. And we say that the small cell base station is capable of caching M bits of data. Now, usually the concept is that this M is much lesser than the size of the entire library, right? If M is almost as large as the entire library, then we don't have a problem. But M is a reasonable size, which is capable of serving the user requests as well. And in caching literature, generally what we do is we study the trade-off between the increasing of this size and how the network parameters scale. So another important assumption is that the demands are IID. From each user, we observe demands at every time instant. And across time instants, we assume that the demands are IID. But obviously, they are coming from some distribution. So the demand is being, it's a stochastic setting, basically, where we assume that the demand is guided by an underlying distribution. And theta F is basically the popularity distribution on the files. And this theta, for each file, will have basically one value of, or you can think of it as a probability distribution on the files being requested from the small cell base station by the users. Now, our main aim in this process is to employ reinforcement learning to actually estimate the theta. Right? When you start the process, you don't know what these thetas are. If you are given the theta, then you can place some content. But if you don't know what the thetas are, you need to formulate a process to learn these thetas over time. Let me go back to this figure once again. So there are two aspects to this problem. One is how do you learn the thetas? And the second aspect is given the thetas or given these popularity profiles or the popularity distribution, how do you place content in these in the cache, right? Based on this cache content M. So you can only cache M bits. How do you actually place the content in these files, in these caches? So first I'll talk about the second half of the problem because that is easier, and then that will tie back into the learning part or how we estimate the popularity profile. So There are two concepts in cache placement. One would be uncoded caching and the other would be coded caching. Now, uncoded caching assumes that you are allowed to place only full files into the cache. So if you are given m bits, you can divide the m bits any way you want, but you can only place entire files. You cannot place arbitrary fragments of files in the caches. So that is the meaning of uncoded here. There is no channel or network coding right now. And we define the cache placement by some variable, say x, which is indexed by the number of files. And we say that the x is 1 if the file is cached and it's 0 if the file is not cached. And that ties into the cache constraint where we say that the size of the file multiplied by x, and if you sum it over the entire library, it needs to be less than m, which is basically the entire cache size. So this is the uncoded placement. Now, there's another concept of coded caching. The alternate way of doing this is, now I will talk about this later, but even though this problem on the left looks easy, it's essentially not. You cannot really solve it optimally under any general circumstance. One alternative is to do coded caching, where you say that we take this library of files and we'll pass it through a rateless coder or a fountain code. What that does is it basically subpacketizes each of the files. Now you can think of the packets of the files as some fraction. So essentially, a fountain code does not have a total length. So it's not a concept like NK code. It doesn't have an N. It just has a stream of packets coming out of the code. And you need to collect just K of these packets to actually decode the file with a very high probability. So the fountain code is a good application, and it is applied widely in video coding nowadays. Raptor codes, for example. And it's a very good application for this because you can now think of the file placement as a fractional property and not as a full file placement as a 0 or 1. So now if you look at this file placement, here we have a variable row, for example, which is the fraction of the file that is cached. If row is 1, the entire file is placed. If row is not 1, then basically only a part of the file is placed, right? And essentially what happens is if you place a part of the file, you then download maybe the remaining part from the main base station, or if there are multiple base stations, then the K helper concept comes in, which is a very popular concept that one user is connected to multiple caches, and he can choose to download parts of the file from these multiple caches, which is essentially the femtocaching framework, which we will talk about. So you can think of the uncoded basically like a convex relaxation of the coded as a convex relaxation of the uncoded placement, where you basically remove the constraint on the storage variable x to being between 0 and 1 and not to be 0 and 1. We won't talk about this much because this is a convex optimization problem. Not trivial, but it can be solved optimally. The more interesting question is what happens with uncoded placement, because as I said, Raptor codes, even though they are popular, it introduces a layer of complexity into the system, which you want to avoid if you can, right? If your system performs as good with uncoded, why would you want to do coded placement? Now, uncoded placement essentially ends up becoming something we call a knapsack problem. So it's basically fitting zeros and ones into the cache so that you can satisfy the entire cache constraint. And it is essentially an integer optimization problem. So given the fine popularity profile, okay, that fs belongs to f. I don't know, there's something wrong with this slide here. But the main optimization problem becomes this. Now we will talk about the structure of this optimization problem next. But the main optimization problem that you want to solve in order to maximize the cache hits becomes this. This is very simple. So this is just saying that this being the popularity of the file and this being the size of the file, you basically want to maximize the largest, most popular file that is placed in the cache, right? So if SF is very large, that also has a weight in it. So if a very small file is very popular, you will place it. But if a very large file is almost as popular, you would give that preference. So it is essentially a sort of a reward function where you are saying that if I place this file, I get this much reward from the users because you get more data downloaded from the caches and with a higher probability. So that is basically the rationale behind it. And we will go to the next part of the talk and we'll see why this is a good choice for an optimization function, like an objective function. And obviously the constraints are the cache constraint and the placement constraint. But this is an example of a knapsack problem, as I said, and yeah, sure.
So theta sub f is not a stochastic variable, right? Just
Sorry?
Theta sub f.
For this setting, it is not. For this setting, it is not. It is given. You are assuming that theta sub f and SF is given. But for the entire system, it changes. Because theta sub f is basically the popularity profile that you're trying to estimate. over time. So it becomes a sequential optimization problem rather than a one-shot problem. So I'm just talking about the one-shot problem right now to throw better light on what happens when we actually start learning this theta. So even this simple problem is NP hard, and a solution obviously exists. You can do greedy solutions. Yeah.
So could you have used any monotone function of SF, or is there a more fundamental reason for the choice of?
The main reason for this choice is basically will be highlighted in the next section when we talk about coupling of the learning process with this, because this part is basically what the learning process observes, right? When you place caches, content in caches, the learning process basically is observing what content is downloaded from the caches. So yeah.
Is that a good metric?
Which one?
Theta F into SF.
It's a simple metric, I would say. It's not the best. There's many open debates about these things, but it's a good metric when we couple it with the learning process. It satisfies the properties that we want in the learning process, essentially. But it's essentially simply just saying that if the file is of high popularity and of high size, we'll like to place it in the cache to get it downloaded. That's about it.
Because even if the popularity is low, but the file size is high, you're caching it. So
generally, okay, so that becomes a pattern of the popularity profile. Generally, we use distributions like power law distributions or ZipF distributions, where you have very few files of high popularity and all the others are sort of lower. And I should actually mention that this work is done under the assumption that the popularity is a ZipF popularity profile. So essentially that the main mass of popularity is occupied by maybe if you have a library of 1,000 files, 200 files will be most popular, and then all the others will tail off exponentially.
then will you actually cache the highly popular file, because if the variance on SF is high,
Yes,
and if
so
you have a lot of files that are unpopular, you may end up caching only. I just
yeah. So the thing is, these things are basically based on some experiments, obviously. So you don't expect your files to be widely ranging in sizes. Like it can't be a 1 MB file as opposed to a 100 GB file. That's what I'm trying to say. So we are mainly talking about uniform types of files, for example, videos or movies from Netflix. So obviously there is a gap on the variability of SF. If it's like very vast and even the popularity profile is very vast, then I believe this problem will slightly break down. But even then, I believe this is something good that you can do. Other than that, you have to base it on the instantaneous popularity profile, right?
But if you choose SF or function of SF such that the expectation of theta f SF is a constant, then that problem will not come.
Yeah, so now we are talking about sub-packetizing the files, right? So you can choose equal size packets if you want.
Right. No, you are trying to match SF to the demand distribution.
Yes.
Because right now, no matter whether the
But how
demand
will
is ZipF, your objective function, part of the objective function, which is SF, it's just arbitrarily chosen. Although there is a probably more fundamental reason which we can discuss towards the very end.
Yeah.
But you can choose a function which is essentially monotone in SF that matches to the demand distribution such that the mean of theta and SF is a constant, and then you are essentially just saying that if there is a file that is very popular, and even though it's smaller, right? So you're essentially saying that the number of bits for a very popular file and a short file is essentially the same as a very large file with appropriately weighted popularity.
Appropriately weighted popularity.
So
yes.
Here, then you will have an objective function that is matched to your popularity distribution.
Yeah, so basically, again, this theta f, right here, the theta f, it's actually an expectation of the demands of the users taken over a time scale.
So this is
so what you are doing here is maximizing an average sort of downloaded data function. This is not a one-shot function. So I guess the way I'm talking about it, this is looking like a one-shot function, but basically what you are doing here is you are solving this optimization problem over a length of time, and you are trying to converge to a distribution.
Right, of course.
Right. Yeah. But I understand your question. I mean, I agree that you can do something different, and that is one of the points that I have as a maybe direction of future work in this area. Yeah. So moving on, the only way you can actually optimally solve this problem with a high confidence is when SFs are all ones, and or each file is of unit size, or each file is of same size, essentially. If all the files are of equal size, then you can solve this problem optimally by doing a greedy approach. And I won't go into the details of this, but I mean, this is a very common knapsack problem approach which you can see online. So this leads me to the other direction where the study of approximation algorithms comes in. And it's a very important topic, I believe, because it guarantees some sort of approximate optimality on greedy algorithms for really hard optimization. So this problem does not look hard, but it is in general, and it gets harder as you increase the dimensionality of the problem, which we will come to in the next part. And again, some buzzwords I would like to throw out are matroids and set cover, so you can basically look at these problems under different settings rather than just this stochastic type of optimization problem. So you can think of this problem as a optimization or minimization of a submodular function with some matroid constraints, which is what the other body of work that does not involve any learning does. And you can derive some guarantees on the approximation, although it is to be taken with a pinch of salt because all these guarantees are only valid when all the files are of equal size. You cannot really guarantee optimality when the files have vastly varying sizes. So this is what it ultimately comes down to. And I think that is an okay assumption for now because you can always subpacketize your files and divide it into equal size chunks and call them different files, right? And then deliver it that way. But it becomes a problem if the library is very large and you have many equipopular files, for example, that you have to break into different things, and it kind of becomes as complex as doing the coded cache placement. And again, for this problem, game theory is also an alternative approach, and Dr. Saad here has done some work in the past on many-to-many matching games, where you basically, I'm not very familiar with that area of work, but many-to-many matching games, mean field games, and auction games are generally often used under this framework to decide what content to actually cache based on what sort of popularity profile. So this is a weighted optimization problem in some sense. You can think of the theta f's as some value or weights on each of the files, and if you consider all the files are equally sized, then theta f is the only parameter over which you need to optimize, right? And you can cast it into a game theoretic framework as well. So optimization is not the only answer, but for us it's a good answer because of what we are going to talk about next. So the learning process in this framework is very important. We need to have a learning process which basically over time gives you a very maybe a confident assumption or a confident estimate of what these popularity profiles are. And for this purpose, multi-arm bandits is a very nice framework, I believe. So we will talk about what is a multi-arm bandit in some detail. So as you can see, multi-arm bandit is an octopus playing slot machines. But what it ultimately comes down to is that suppose you are this octopus and you have multiple hands and you're sitting in front of, say, multiple slot machines, say n slot machines. How would you go about playing these slot machines, right? That is the main question that the problem asks, the problem framework. So you decide on a game that I will play maybe, just to start off with, I would like to, if I'm a very smart octopus, I would like to play all the machines once and look at what sort of rewards I'm getting from those machines, right? And then based on maybe, if I'm a not so smart octopus, I'll just keep choosing the arm that gave me the maximum reward in the first round, and I'll think, oh, I'm doing a good job. But that might not be the best strategy, right? So the question is, you want to play a different slot machine with you. You're capable of playing a different slot machine with each arm, but you want to also play the slot machine such that you maximize your winnings over multiple turns or multiple time instants. So, for example, if you have a time scale of 1 to t, you want to play the arm such that you maximize your rewards from these slot machines over that period of 1 to t. And in general, this framework is a class of Markov decision processes. I won't go into many details of that, but there are two types of bandit problems that are in existence. One is a stochastic bandit problem, and one is an adversarial bandit problem. So in stochastic bandit problem, what we assume is that suppose we are playing the slot machines, right? So we pull a slot arm and we observe a reward, or we get some money back from the slot machine. So these rewards, we will assume that they are IID across time. There's an underlying distribution that is guiding how these rewards are generated, but they're IID across time and the machines. So this is the stochastic setting. And another assumption here is that my reward in the previous round does not really have a lot to do with the reward in the next round. Obviously, if you learn the distribution, it has something to do with it, but in general, as far as the distribution is concerned, they are independently distributed. Now the adversarial bandit setting is more interesting, where it says that, okay, now the owner of this casino has figured out that you are smart and he wants to target your strategy. Say you chose some policy to play these arms, right? You are very smart, you choose some policy. Now the owner of this casino decides that, okay, I will counter this policy by making sure that the slot machine you play does not give you the best reward that you hope for. So the stochastic setting assumes that there is no strategy in the rewards from the slot machines. They are just distributed stochastically. But the adversarial setting assumes that there's an adversary sitting behind the slot machines who basically controls how you get your rewards. So this is a very pessimistic setting in general. And both these processes, so we will talk about the stochastic setting, but both these processes are in general guided by two notions of what we call reward and regret. So what essentially is a reward? Reward is nothing but, so again, going back to the slot machine example, you get some money back, so that's basically your reward. And you want to maximize your reward over time. But if you just look at reward, it's not the best metric because there is nothing stopping you from just getting arbitrary rewards and hoping they're the best, right? So you somehow need to figure out how bad is the best that you've obtained, right? So the only way to do that is if you know what is the optimal strategy, right? For example, you know that if I follow some policy, arbitrary random stochastic policy A, by choosing some arms over time, I will get the optimal reward. And now someone else follows a policy B, then you can basically decide that how bad is your policy B compared to the optimal policy. And so regret is basically defined as the difference between the expected reward of a given strategy and the expected reward of an optimal strategy. And by expected, we mean expectation over time and the random choices that you make while you select the arms. As I said, it's basically the notion of competing against the best action that is possible. So if you take the best action, your regret is 0 and your reward is maximum. So essentially, in practice, what we try to do is we try to decide how to do best against the best feasible strategy rather than the best possible strategy. For example, if it's a true randomly distributed rewards, you really can't hope to learn it, right? It's a true randomness. But there is something that is feasible and there is something that is infeasible. So we always compete against the feasible strategy. So we'll introduce some notations here. So we'll say that there are some actions or machines, for example, which are indexed by 1 to n. And each machine has some reward x associated with it at time t, where t tends from 1 to t for a given window of time. And we'll say that the ensemble mean is basically the expectation of the, or actually xn is the true mean of the rewards. So the rewards are stochastic, right? So they are distributed according to some distribution which has a mean, and that is given by x hat. And we say that the best action is n star. So you choose that arm which always gives you the best expected reward, right? So basically that will give you the maximum of the mean reward, which is x hat star. And then we define the concept of a cumulative expected regret, which is essentially the difference between the maximum expected reward that you get and the reward that you get by playing some policy A. So that A is some policy that you have decided, which chooses this arm IT for every dimension. So say at dimension 1, you choose machine 1. So that is your IT at dimension 1. And then you go on and you choose your machines and IT defines that. So this is essentially a system parameter which we define in order to design the algorithm. So the best policy design is to minimize this cumulative regret over time. So this is indexed by time, as you can see, and within a finite horizon, my choice of policy would be to design that which minimizes this regret. And the algorithm that I'm going to discuss next is basically called optimism in the face of uncertainty. So basically, when you're faced with uncertainty, make the most optimistic choice. And that gives rise to the most interesting concept in this sort of problems, which is called exploration versus exploitation. So I'll give a small description of what that is. So for example, again, going back to that octopus, if you have this one machine which you decided gave you a good reward. If you are not a very smart octopus, you will try pulling that same arm over and over again because it maximizes the mean of that particular machine over time. And you won't really go after any of the machines that have a smaller mean. Now the problem being that when you start with a bad machine, you haven't sampled the whole distribution enough to understand whether any of the other machines are actually good or you are just seeing a random pseudo sample of some machine, right? So ideally, you wouldn't want to trust just the means, right? If you just want to maximize the means, then you are biased towards those means and you're biased towards your observations. You would try to maximize the whole distribution. So therein comes the concept of exploration. So you want to sometimes pull some arms just to see what rewards they give, right? So, okay. I don't think I'll finish in time. So the cool part about this algorithm is that it takes the concept of exploration and exploitation and basically designs a very simple algorithm. The simple algorithm just says that assume that the machine n gives you a reward of x bar n over time. You basically add this small parameter here, and you always play that machine which maximizes that particular expression over there. So this first part is exploitation because you are exploiting the actual rewards you are observing over time. And the second part is called exploration. Now this Tn that is in the denominator is basically the number of times you have sampled that particular machine. So the more the intuition here is the more you sample a machine, the more confident you become of what sort of rewards you might get from it, right? But you also don't want to discount all the machines. You want to sample all machines enough number of times so that you get a true distribution. And so the theoretical dependence of this algorithm is on the Chernoff-Hoeffding inequality, where we say that if you have a set of random variables, say y1 to m, which have a support set of 0 to 1, and these are the expected values. So these are the true means of that distribution. So basically, capital Y denotes the ensemble mean, and mu denotes the actual mean of the set of random variables. So the Chernoff-Hoeffding inequality says that basically you can give an upper bound of the probability of how much the ensemble mean, or what you have observed, will deviate from the actual mean. And this is an exponential bound. Now, so this is basically a concentration inequality which shows you how a random variable deviates from its mean or converges towards its mean. Now, the cool part is how you can map this problem to the learning process here. So if you consider y1 to ym to be the reward for any one action, for example. So for any one machine, you have played it m times, for example, and you have observed these rewards. So all my things are kind of misaligned for some reason here, I'm sorry. But basically the concept is that you choose this upper bound value, a, in a certain way, which gives you a very good confidence on the probability that the mean that you have observed is not deviant too much from the true mean. And that's a good guarantee to give, right? So if you play a policy which tells you that your ensemble mean is not varying widely from the true mean, you are in good shape. And that is exactly the point of choosing A as this parameter, which you will see reflected over there as the exploitation parameter. So a simple way to look at this is you choose an A, which gives you a pretty good bound on it. So basically now you see from this equation that the probability of the ensemble mean actually being A away from the true mean is exponential in the time slot, or exponential in time, like it decreases to the power of -4. I think this is a very simple explanation, but there are many nuanced topics for this proof in general, why that is like a good thing to do. And one of the main concepts is that the cumulative regret, by doing this, you can prove that the cumulative regret decreases logarithmically in t. And it's just basically saying that if there are actions which differ in optimality by a wide range, then you don't need to sample too much, right? So if your action 1 is very optimal as opposed to some other actions which are less optimal, you can just get away with sampling action 1 a few times and you'll figure out. But if everything is almost equal popularity, then it's more harder to learn, right? Which file is more popular or which arm is more popular.
So is there a specific reason to bound it by t to the power -4, or you could?
So this algorithm chooses t to the power -4, so it basically ties in with the fact that you use 2 over there in the logarithmic term. So you can tighten it to something else if you want. But it is believed that t to the power -4 is a good roll-off factor. Like the roll-off, you can do -3 as well, you can do -2 as well. But 4 is kind of good. 8 is better, 10 is better. But yeah, so this is the general learning framework that we are using. And this ties us back to the learning-aided caching problem. And in caching now, we will try to basically map this problem to the placement problem. And we go to something called combinatorial map. I won't discuss too much in detail about that. But the concept mainly is that instead of playing just one slot machine, the octopus can basically play multiple slot machines. So you can think of an F-armed bandit, and you can think of a library of F files, and each of the arms basically map to one file, right? And so pulling a slot machine corresponds to caching one file. So it will cache only those files which will optimize the reward or minimize the regret, for example. So you have this cache, and then you play the super arms. The super arms are basically a collection of multiple arms, and you cache m bits. And here we again come back to this concept of the reward, which you are trying to maximize. So this ties into the concept of minimizing the overall regret. This is why this is a good choice for this learning mechanism. And you basically observe the rewards on the cached files, and you learn theta f with the map over a period of time. And you can show that it converges to a certain popularity distribution. Again, this is the extension of that framework to the cache-aided network, where you see that if theta hat f is the actual mean of the popularity distribution, the ensemble mean, you do an exploration based on the second part, and you're just not exploiting but exploring as well. So again, here we assume that the popularity is web distributed. And one important assumption here is that in this framework, the learning process actually assumes that you optimally place the files, because when you're playing slot machines, you observe the reward, right? There's nothing ambiguous about it. You play an arm and you observe the reward. Here, there's a placement process going on. When you place the files, the reward is actually what the users download after placing the requests, right? So the map problem essentially assumes that this placement is optimal. So there is a nice trade-off between how optimally you can place content and how well you can actually learn in practice. So if your placement is optimal, you learn the best. But obviously we can't do optimal placement, so that becomes a trade-off. Now, I guess I'm pretty bad on time. Yeah.
Isn't the reinforcement learning in a better framework?
So this is a reinforcement learning technique.
No, I mean when you don't know the reward associated with each state, so you consider a distribution for instance, you take action and go to a state and observe the reward, and based on that reward, you actually modify.
That's exactly what we're doing, right? Exactly what we're doing. So basically, the map problem is happening over time, right? So if you look at this algorithm, it basically observes what is cached, how much the users have downloaded. It updates at every time instant. It is basically updating its estimate of that theta based on what has been downloaded, and then it's adding the exploration parameter here, and then it's moving on to the next round. So it's placing content based on that updated parameter. So we call that a CMAP index, basically the theta bar. So that differs from the theta hat, which is the actual true mean. I guess, so how are we doing? 1 minute? You're done? Okay. Yeah, I had estimated 50 minutes for the presentation, but I guess I got 40. So it's fine.
Is there something planned in this room, or can we continue for like 5 more minutes? Or
We
do
can probably
know?
keep going, but we don't know. The
We don't
scheduling
know.
system doesn't tell us.
Oh, I see.
So
Okay, so.
Let me see if there is anyone outside. You can continue.
Okay. So the framework that we actually contributed to in this, whatever I talked about is actually already in literature. But the framework that we contributed is collaborative caching. So here we assume that there is a multitude of small cell base stations rather than one small cell base station, and how you jointly place content in these caches. So as you can see now, the placement variable becomes a two-dimensional one, because there are these F files and then there are n small cell base stations. So how do you place content in this two-dimensional case? And I think this problem is general in the sense that you encounter this problem in any, say, scheduling problem for OFDM or anything, wherever you have slots and resources. So you can think of it as a time frequency grid as well. And the theta fn also becomes a two-dimensional variable here for each file and each base station. Obviously, this again turns out to be a very hard problem to solve, and the general class of problems is called generalized assignment problem. And it is NP-hard, where you can basically show that if you take this example network where everyone is connected to every base station, it becomes a big caching problem with all the base stations together. So it's the same problem that we talked about in the one base station case. And this is another network example where there is no interconnection. So it's a collection of n such problems. So all these problems are NP-hard. So overall, the problem can be proved to be NP-hard. So in CMAP, I guess our contribution is essentially to propose a new update procedure for the ensemble mean. And I guess it's a lack of time, but we'll just go ahead and look at the results. So we basically propose a per user reward function here. So we have seen that we cannot do a per base station reward function, like just the simple summation over the users connected to one base station, mainly because there is a topology here where multiple users are interconnected. And the problem is still NP hard, obviously. So I'll skip over these parts and I'll basically just talk about some interesting aspects of the problem. So the main question is whether you want to collaborate or not. So it turns out that obviously collaborative caching, when you do it across multiple base stations, it gives you a performance advantage over non-collaborative caching, where this is you're learning locally over each base station. And this blue curve is basically a curve where you are given the distribution. So if you know the true distribution of the demands, the blue curve is what you will achieve. So it does not change over time because you already know the distribution. And you can see that the red one converges to it. And in some cases does better because of the cache constraints. But it basically always converges to it. And the black one up there is like the holistic bound where you say that I know the instantaneous demands and not even the distribution. So that always does much better. And here on the right, we have a case where the left one is basically almost uniform popularity. So the file popularities do not differ by much. So you see that it is much harder to learn and it ends up giving you less reward overall. Whereas if you have a skewed popularity profile where only 1 or 2 files are very popular, then you learn much faster and you actually even do better in both cases than the informed upper bound where you know the distribution. That is because you can very accurately place all content and account for local variability as well. So that is some of the things that we have seen. Another interesting concept that we have observed is the fact that network connectivity matters a lot. So if you are in a very dense connected network, we see that local and global caching or collaborative caching differ by a lot. For example, the blue curve and the red curve here, they differ by a lot. Whereas here, when you move to a more sparser network connectivity, the gains kind of disappear. And another interesting concept that I would like to note is that if you look at the uncoded caching here and the coded caching there, so coded caching is again going back to being able to place fractions of files. I didn't go about it in detail, but the uncoded caching, you are placing whole files. And the learning process is basically learning based on what you have placed, right? So you can see, surprisingly, the uncoded even performs better than the coded. And this interesting result is because of the fact that by placing full files, you are making life easier for the multi-arm bandit to learn the actual popularity distribution rather than placing fractions of files in the caches, where maybe it's optimal from the cache placement point of view, but the joint placement and learning is not that great because you're making it very difficult to sample the distribution enough, right? So these are, I guess, some thoughts. We can basically, one important aspect here is that in caching, we can potentially observe more than the multi-arm bandit because the multi-arm bandit plays a slot and just observes that reward, right? In caching, once the base station sees the demands, it can potentially have an observation on the entire library. So it can think that if I had placed some other files, what would have been the reward, right? So there is more information involved definitely in this framework rather than just the map setting. So the main question is CMAP the best setting? So we have worked on this framework. We know it's a good algorithm. It solves stuff, but is it the best setting? I believe not. But it then becomes a computer science question and it kind of goes into the learning domain where you have to do something to prove that this is not the best one. Another question is, as I said, how is the suboptimality of cache placement directly affecting the accuracy of the learning? Because they are interconnected, right? So we have seen that with optimal cache placement, you still make life hard for the map to learn properly. And I think the most important question here is, what is the theoretical dependence of the topology on this learning process itself? Because we do it for one shot and we observe things over time, but what if it becomes a probabilistic connectivity model? Then how do you incorporate that into an overall learning process? And again, finally, can we formulate a better reward function, which is tied into all the questions that we had. So I guess I will not cover the last two topics here, which is mostly an information theoretic framework of caching, which has been my PhD work overall, and the fog radio access network. So if you guys are interested, we have papers on arXiv, and we did some interesting work where we looked at end-to-end latency in such networks, and it kind of directly ties in with the kind of system models that we talked about here.